I know it feels like a very clickbaity title for a YouTube video. Unlimited, free, no account required. But it's real. It's actually real. And when it's real, is it still clickbait? I don't know. You can decide. It's called Sendme. It is free and open source. You can go to this website right now and download it and play with it. But you can kind of think of this like AirDrop, but it works anywhere in the world and cross-platform. And we can go one step further than that. This can be the kind of thing that you sew directly into an app that you build. And we're going to show you how to do that today. Today, we're going to do three things. We're going to show you Sendme in action. We're going to explain how this free, unlimited, no accounts thing is possible. And then we're going to show you how to build it and put it into an app of your own. Using Sendme is pretty straightforward. Download the command line tool, pick some files you want to share, send somebody a ticket, and they will receive it and download it. And it's that simple. So let's actually download and use Sendme. So I'm going to go to this website, click this copy button, come to a terminal, paste. It is going to download. We're then going to do Sendme, send, and I'm going to send the Sendme binary because that feels right. And great, I'll take this ticket. I can take that, paste it, send it to somebody else. They will take it and type Sendme receive. They'll paste in that ticket and it will initiate a direct connection. So let's do that now. And just like that, we've moved the Sendme binary itself from one computer to another via a direct connection. Okay, so how are we able to do this with no accounts and free forever? You're probably, if you've been watching this channel, you probably know how this trick works. It's with direct connections. Because these two devices are connected directly, there isn't any overhead involved. Iro's going to do a bunch of work under the hood for hole punching to actually get the connection established. But once that happens, there's no reason for you to need an account. The Sendme tool just relies on the existence of the key pair infrastructure to know that you are person A and you want to send that ticket to person B. And that ticket that you share around is kind of your whole credentialing password system. If you give that to someone, they will be able to download from your computer. And if you don't give that to people, they won't be able to download it. And your control over the downloading process is as simple as just closing the app. And as soon as it's closed, no one can download from you anymore. So there's not a lot of permissioning. So part of this is that it's very simple, but also this is a really incredible foothold for a better user agency story. You're actually able to provide a much better guarantee than you would in a system that has to be backed by cloud infrastructure. That's not where we want to stop. Great, you can send files. That's really exciting. And it proves out a nice model, but wouldn't it be nice if you could put this into an app of your own? So let's do that ourselves. Today, we're going to walk through a really quick example of how to set up a version of Sendme yourself. The actual Sendme code itself is open source, and so we can go through that right now in github.com, number 0 computer, Sendme, and I will show you the source code now. It's one file, main.rs. That file is 895 longs long. It's, it's no child's play. The actual Sendme binary includes the stuff you need for resuming transfers and for progress bars. Those are two things we're not going to cover today. But both of those, if you want to get into details on how to do progress bars and resumption, that's really great inside of the actual Sendme binary itself. Okay, so let's build this. Today, we've cooked up a really simple example. Psst, this is actually just the quick start from our website. We're going to walk you through it. I'll link you to that too. Okay, cool. Moving on. Today, I'm actually going to type you through this tutorial instead of just copy and pasting everything. But this will be a nice chance to explain Sendme kind of in a basic form. Sendme is built on top of the Blobs protocol, and the Blobs protocol uses something called content address data transfer for verifying things incrementally. We're not going to get too much into the gory details of content addressing today. I think that's going to be a fun surprise for later when we start doing increasingly sophisticated and interesting stuff with Blobs as we go. And we're going to start the same way we did with the gossip chat version, and we're just going to do cargo init Sendme tutorial. I have to call it Sendme tutorial because I already have Sendme on my machine. All right, now to get started, before we even do anything, we could actually do cd Sendme tutorial. And cargo run. Hello world, fascinating. Okay, let's get an editor open. So opening this in Z, I can see now this source file here. Code editor's open, we need a few crates. These ones we're gonna add with cargo add. We're gonna start with iro, duh. Today we're going to be working with the Blobs protocol. Blobs is what's going to provide us with the actual data transfer tooling. So we're going to do IRO blobs, and we need a feature from Blobs. So we're going to do features, and because we're doing multiple, we're going to do IRO multiple crates in the same invocation. We're going to do IRO-blobs/RPC. RPC in this case stands for remote procedure call, and the remote procedure calls we're going to be making today will actually be in memory. It's a little bit confusing, but we use a Flume channel, which is a Rust concept, to talk in memory between the IRO blobs protocol and actually invoke things on that protocol. And then we're going to need a few other crates. We're going to need anyhow, and we're going to need Tokyo. Anyhow is the errors thingy, and Tokyo is the runtime thingy. Great, runtime thingy, errors thingy, highly technical. Moving on. This is going to do editor GAC in the background, and I'm going to go back to main.rs and add a few things to our hello world. First, we're going to drop hello world, get out of here, and we're going to do Tokyo main. This turns it into a Tokyo main, but it needs to be async, and it needs to return a result. And the result, I don't want to use the standard library result. I want to use anyhow result, which is a capital R result. And that's going to be a result of nothing. And then we're going to make the compiler happy by saying, hey, okay, let's return okay. And I have to do use, because that's how we use stuff in Rust. Great. Okay, now we need to actually do some IRO stuff with this. So we're going to use the IRO endpoint. And then here it's going to be let, and oh, even, thanks AI thingy. This is pretty close. Endpoint is going to be endpoint builder. So we need a builder. We're going to turn on discovery_n0. This is going to turn on the ability to do DNS discovery of IRO nodes via identifiers. There's more on that in the quick start guide that's linked in our documentation. But basically, you just want this. Okay, cool. Turn that on. We are then going to run this? Sure, let's run it. Cargo run. Are you happy, compiler? The endpoint is unused. Yes, we know that. Thank you for the warning. Okay, that's good. We've got a good starting point. Okay, so next we need to add the Blobs protocol. We're going to eventually create a router and provide the protocol to the router, but first let's just build Blobs. And to do that, we're going to use IRO blobs, and we're going to go into the net protocol module, and we're going to get the blobs thingy. And today we're going to work with blobs in memory. The file system one is the one that you would normally use in a production setting. The full Sendme source code uses the file system version and creates temporary directories, which you can find and track on. But today we're going to work in memory because it's faster and easier for demo tutorial purposes. So let's do blobs, and we're going to do blobs memory, and we're going to build it, and we're going to pass it a reference to our endpoint. And great, that's enough to get started. Once again, cargo run. Are you happy? Great, it's working. Now that we have our blobs functioning, we've compiled this once, and we have this squiggly yellow line that says, hey, we need to use blobs. Let's use blobs. Let's do what the compiler wants us to do. Most of Rust is just doing what the compiler wants you to do. All right, so for that, we're going to need a router. And so I'm going to do the IRO protocol router import. Now, I'm using my IDE to navigate this, but if you ever need, you can always just go docs.rs and search the IRO package, and you can search around for yourself for things like router. It makes it a little easier to explore. But let's create a router now. So we're going to do let router equal router builder. And here we're actually going to pass it the endpoint. So we're going to pass ownership of the endpoint to the router. And that is indicated in Rust with these ampersands. An ampersand means I'm passing a reference to you that you're going to give back to me after your function is done. The no ampersand means you're going to own this. And now it's on you. If I try to use router here, or if I try to use the endpoint here, sorry, it's gone. It's now owned by the router. And so I'd have to talk to the router to get a reference to the endpoint if I wanted, which I can do, but we're not actually going to. Anyways, we're going to not register build. This is AI GAC. This is going to, first we're going to accept on the IRO blobs ALPN, which is the application level protocol name for the blobs protocol. And that's registered with blobs. If we go look at this, you can actually see it's just IRO bytes 4. This used to be called IRO bytes, but now it's blobs. Names change. And then we're going to do blobs.clone. We need to pass a clone because we want to keep the blobs protocol around and own it because we're going to use it as a client in a second. Then we're going to spawn this thing, and we're going to wait for that to happen asynchronously. We're going to type a question mark so that if anything goes wrong there, this whole main function is just going to bail out. And okay, Bob's your uncle. Cargo run. Who is Bob anyways? I don't know. It's beyond the scope of this tutorial. Okay, cool. It runs. Now our router is unused. That's fine. Leave us alone. Let's actually use the Blobs protocol. And so let's do blobs.client. And this is the thing that we needed the RPC feature for. And so the client is now going to let us do stuff. And if we type client here, you can actually see that we have like add bytes. So that's where we add a sequence of bytes to the Blobs protocol handler. And then we also have stuff like download, which will let us download from other folks. And before we get any deeper, we should talk about a little bit what happens with Blobs and how it works and what it does. So when we do client add bytes, we can examine the function here and we can do bytes, you know, the usual hello world, and await that and look at the result. And the response is going to be an add outcome, which has a couple of things in it: a format, a hash, a size in bytes, and a tag. We're going to not talk too much about tags or formats today, but we are going to talk about that hash thing. Specifically, it's Blake3 hash. This gives us a couple of very important properties. First and foremost, it means that we get something called incremental verification out of it. This is very useful for when you're trying to resume a transfer. Incremental verification means that as data is both flowing out from the send side and in on the receive side, we are calculating the hash incrementally of the values that are passing in 1024 byte increments and checking that that matches the expected hash that we used to refer to that data in the first place. So when you actually send a ticket from one Sendme instance to another, the ticket is that thing that you're copying and pasting, it includes the hash. It doesn't actually include the file names or anything. It just says, hey, I want this data, and it's referred to by this hash. And because you're passing a hash, we can then use that to confirm that the data you're getting is actually the data that you asked for. The Blake3 hash function has a thing called a Merkle tree inside of it, and we use that to actually confirm as the download is happening. It gives us two things. First, it means that we know right away when that data is either corrupted or wrong. If it's not the thing you asked for, you will instantly know. Secondly, if that connection or that transfer is broken, we can pick up from where we last left off just naturally. Because we know that, hey, we have these things and these things match, we can naturally check the integrity of that data on both sides and figure out what is or is not corrupt. Very useful property, right? There's lots more to talk about with the Blobs protocol, and Rudiger from our team will get into that for you on this channel. But for today, those are the things that are really worth knowing. We're going to pass around stuff by hashes. We're going to use those hashes to get magical properties as we're working with this data both on send and receive. All that's going to happen with the Blobs protocol under the hood, and this is what's so lovely about just being able to pull a protocol off the shelf and put it to use like this. Now we're going to play a game of draw the rest of the owl. I'm going to copy and paste in a bit of code here and talk through it instead of typing it all out by hand. It'll make this all go a little quicker. I'm going to come in and just paste in this giant thing. Hit save so that format happens. This giant thing that I just posted is basically a CLI parser. This is honestly some fairly advanced Rust, but what we're doing to talk through it is we are taking a reference to the arguments. We are turning them into an iterator. We are mapping over that iterator. An iterator is kind of like a loop. And then we are looping that map and saying, hey, we're turning that into a string. So now every element in there is turning from a vector into a string. We are collecting those up into a vector, and then we're going to iterate over that in a match statement. Does that sound like a lot? What that's generally making is a giant switch for whatever command line arguments were provided. And there are only kind of two match arguments that we care about. And they are switching on two things that may be familiar from the gossip video. We are splitting up our command line into roles based on, am I the one sending data or am I the one receiving data? And so this gobbledygook is just giving us a very fast kind of clap-free way of doing iteration over command line arguments. And this match statement means we are then just throwing that into a match saying, hey, do you match what I'm expecting? If not, we're going to just print out, hey, this is how you use us. This is a cheap and cheerful CLI. And so that's how we establish roles. Again, it's the same principle as before. We are first going to have to decide, are we the one sending data or are we the one receiving data? And our roles are very different this time because the entire flow of data is going to be this temporal setup and shutdown kind of process. If you're the one sending data, you download Sendme and you say, I want to send this, and you leave the CLI running for as long as you want to send it. If you want to receive that data, you download Sendme and you say, hey, I want to receive this ticket that I got from somebody. Unlike Gossip, where we kind of could float between roles because we're basically trying to just get everybody bootstrapped into a topic, we are only ever in one or the other role. And so that's the first distinction, but this concept of roles remains. The cool thing is either side can assume either role. Again, this is the whole idea of software that can do more stuff on the edge. So let's dig in on the send command, because that's where we're going to start, right? So the first thing we're going to do is we're going to take the path argument, which is expected to be, and if we actually do this, we're going to do cargo run send, and I'll just send cargo.toml. Just to prove that this thing works, we're going to compile some code. It's then going to work, hopefully. Hey, it worked. All right, and so this says, hey, exemplar receive, and then there's actually a file argument here, but this is a ticket that's being provided. And we might as well do a small sidebar about tickets. We talked a little about tickets in the last time on the IRO Gossip chat example, but today we can drill in on them a little bit more, and I can go to ticket.iro.computer, and I'm going to paste in that ticket, and it's going to give me an explanation of what's going on. This ticket format is our kind of opinionated version of it. Tickets, in my view and the view of the team, is that this is a pattern, and the pattern is just kind of glomming together the stuff you need to signal to someone else and encoding it in a way that works as a single string that's easy to transmit. Now, the IRO Blobs ticket format and the IRO Gossip ticket format all actually have like an implementation that you can use the ticket.iro.computer to inspect. And so when we paste this in, the first thing that we'll point to is like a little hack, is we always start the tickets with the actual word of the protocol that matters. So in this case, you can see blob, and then the rest of this happens. But here we have the actual hash, and this is base 32 encoded. There's also hex encodings. And this kind of shows you that we can interpret the actual ticket contents without a program itself. But for the actual construction of the ticket, we're going to do a few things, right? What's going to come in from the send command is the path to the file or directory that we actually want to send. And in this case, because we're only going to take a single blob, this does not support folders because it's a basic example. If you want the full thing, check out the Sendme source code. But we're going to use the blobs client, which we created earlier, and we're going to add it from a path. And so basically that's telling blobs, hey, go pull a file in and pull a reference to it and calculate the hash of it. The in place flag means leave that file where it is. Don't create a copy of that file. We're actually going to refer to the bytes on disk that you gave us, which means if you delete that file, something magical will happen. In a running IRO node process, IRO Blobs will be smart enough with its database to pull that internally and keep a reference to it somewhere else. But that in place means that we're not actually creating a copy of this data. We're referring to that data where it is. Then we're going to wait for that actual construction to happen. We're going to finish it out, which is going to just basically ignore, this is where we would inject all kinds of progress bar handling for the actual ingest process. We're skipping all that by just calling finish. We're going to wait for everything to finish, and that's going to give us an outcome. From there, we're going to create our ticket. And the ticket is going to be first a construction that needs a node identifier. And here we're going to use the node endpoint. Before I was referring to this as router, I've renamed it to node because reasons. Anyways, this node, it also has a reference to the endpoint. We mentioned earlier that the router owns the endpoint, so the node owns the endpoint and can give you a reference to it. And so here we're using that trick to actually get our node ID back. And we're going to take that node ID and feed it to the blob ticket creator. So this is the import that we had earlier from the IRO Blobs ticket module. We have the notion of a blob ticket. And we're going to create a blob ticket with our node identifier, the hash, and the format. The format is used to indicate like, hey, this is going to be a directory or hash sequence or collection. There's a whole bunch of words in that, more on that in another video. But today we're just using straight single file references. And the hash is actually going to be the content that we send over. So when we look at this over iro.ticket.computer or ticket.iro.computer, you can see here, that's the data that's actually being encoded into it. And we can see this, hey, file analyze, fetch this by running. And that's actually what prints to the terminal. And then this just sits here and hangs. And it's hanging on purpose because we're now running a server that's serving this file. Now, that fully concludes the send side. At this point, we're asking Tokyo, hey, if you ever press Control C, that's what's going to bail out of this program. So if I come in here and I press Control C, that shuts down. Great. And we see shutting down printed out because at the very bottom of this source code file, we have the point where we're actually gracefully shutting down the node. Graceful shutdown means that it will close gracefully any connections that it has open, telling them, hey, I'm going away. Every protocol has to kind of handle that itself. That's a whole deal. But this is the nice way to say goodbye. All right, that's the send side. So that was what? I don't know, 17 lines of code. Not terrible. Let's talk about the receive side. The receive side is, I'm going to just fold this up. To start with, let's look at the arguments being passed to the receive side. So we have underscore CMD. That's actually just the word Sendme as a string. Or in some cases, that'll be cargo run. But here we have the receive command, which is allowing us to switch on this statement. We have a ticket that's going to be passed to us and a path that we actually want to send it to. And so the instructions that are given to us from the send side are like, hey, just receive this as cargo.toml. That's really nice. And which is basically passing with the ticket and the instructions, the name of the file. And so the name of the file actually isn't inside of the blob. We're actually just taking the principal bytes of the file and sending those over. And so this extra argument is a way of piggybacking the file name on the thing that you send to somebody. It's a neat little hack. Anyways, that's coming in here and being interpreted as the path that we should actually save to. And so this is the path that we're going to write to. The ticket is going to be the thing that we're going to interpret to. And then we're going to ask the Blobs protocol to download this. This actually kicks off the download. And here you can see us pulling stuff out of the ticket that we need to construct the request. We have the hash, we have the node address, and we're going to pass it a clone. And then we're going to wait for that download to kick off. And again, here we're calling finish, which is basically saying skip all the progress reporting. We just want to actually download everything and get to the end. We're going to wait for that to happen. We have finished that download by printing out to the terminal that we've finished the download. Basically, once we've hit here, everything's good. We then create a file actually at the path at this point. At this point, we have actually loaded only into memory because Blobs is working entirely in memory. Again, if we had a file system implementation, Blobs would write to a special directory if the file got big enough. If not, it would inline it into its internal database. That's a whole thing. If you want to talk more about that, jump onto our Discord and we can answer questions about the idiosyncrasies about how Blobs works. But for the sake of argument, because we're operating in memory, at this point, when we've said finish download, that is just sitting in a block of memory. So maybe don't transfer a file that is more memory, using this toy example. Anyways, we are then going to actually create the path that was passed to us as part of the argument. And we're going to create a file there, and we are going to read from our Blobs in-memory implementation the hash that we're asking for. We're going to ask for all of the bytes. Blobs supports actually fetching ranges of bytes and verifying even these subsequences. We're going to wait for that, and we're going to copy from the reader into the file and finish copying and call it a day. And so now, just to make sure everything holds together and glues and happy compiler and things will send, I will now do the magical, wonderful thing of sending a cargo.toml file from myself to myself on the same terminal, just using the example that we just built. So we're going to do cargo. Typing cargo is hard. We're going to do cargo run send cargo.toml. And that's going to compile and spit out instructions to paste this ticket. Now, because I'm in the same directory, I'm going to do cargo run received. I'm going to do cargo_2.toml so that it doesn't write to the same file. And we'll do this. And that downloaded, finished, copying destination. And you can see in my editor, we've actually created cargo2.toml. This is incredibly interesting and exciting because of just how much you're thickening the client. You're now actually shipping capabilities to the edge that give you meaningful agency in a place where you didn't have it before. The ability to say, free forever, no accounts, whatever file size you want, is pretty magical in my humble opinion. And I hope you enjoy that too. And I hope you will think about all the places you could put this inside of an application, an existing application. This is not a ton of code. This is 88 lines of Rust. doing it the full way with progress bars is 800 lines of Rust. It's not the end of the world, right? Just with this subtle shift of doing direct connections, we completely change the model and we completely change what we can give to our end users. And to me, that's really exciting. So yeah, that covers our tour of the Blobs protocol. I hope you have a lovely day. I hope you see the sun at some point. I hope you get a chance to touch some grass. And I hope you get a chance to establish some direct connections in a way that gives you joy. For now, have a good one. See you on the internet.